off, he'll pick up. So stock is going to be disordered, he told me,
yes,
as he came down. So, yeah, go ahead.
Thanks, Baruni. Can you hear me? Okay, excellent. So first confession, I'm not a mathematician. So anything that I say, take it with a grain of salt. You may be more rigorous in your training, ideas, way of thinking, way of doing. But of course, as physicists, we use maths quite a lot. And I'll try to show you that the field where we are working, there's some interesting maths there, okay? And some non-trivial maths there. And there are still open questions which people are exploring and which keeps us busy. And there are a lot of people across the world who are working on these kind of problems. So let me begin with an anecdote. So last year around this time, I was driving somewhere, and then suddenly my friend called me and said that X has got the Nobel Prize. Okay, so that person was from our field. And of course, it was, of course, happiness because somebody in your community has got the Nobel Prize, which is the biggest recognition in your field. But it's also surprising because the physics or the problem that we are working on is not a closed problem, in the sense it's not a solved problem. Typically, you give a Nobel Prize for some problem in which it is a solved problem, right? So in our field, it's in this field of disordered systems, it's not a solved problem per se. But the reason that this person was given the prize was because he had given some ideas and techniques which originates from our field, but has now been used across a large variety of other fields. So basically, it has become a very powerful technique or tool that has made life easy for a lot of people across different research areas. So, and that tells you that how ideas or techniques that are born in some field, let's say, can find its way across different fields and become useful. Okay, so for example, I mean, in maths you are using, I mean, there are a lot of things that you are learning, and so some specific technique or some specific way of doing a problem or solving a problem may become useful for some physicist, for some chemist, or some biologist. Okay, so you don't know initially what would become interesting. So it's just that by chance some method or some problem would become successful somewhere. Okay, so what were these? What was this prize on? So the guys who got the, I'll try to organize myself, although the talk is on disordered systems, I'll try to organize myself. So this part I'll write some buzzwords, which we will keep coming back to. So broadly, the Nobel Prize in 2021 in physics was given in this idea of complex systems. So remember, my title of my talk was Complex World of Disordered Solids. Well, actually, I can just replace this with systems, but I just gave it solid just to have some physical connection to whatever the world that we live in and so on. Okay, so the guys who got the prize were these people. I'll just write their names. Is Manabe, Klaus Hasselmann, and G. Parisi. So these people were for weather modeling, let's say, broadly speaking, or climate, physics of climate. And this person is more from the physics of glasses. So as you can see, it's already that these two people were working in completely different things, climate, weather modeling, so on. And this person is working on physics of glasses, like glass, the glass in which you're drinking water and so on. So completely different things, but the common thing that binds all these people together is this idea of complex systems. Okay, so what are complex systems? So I'll first write down some examples. from Wikipedia, and then we will see why these are complex systems and so on. Okay. So Wikipedia's examples are the following. Climate. Okay, then 2 organisms. 3 human brain. 4 infrastructure. Then 5 socioeconomic organizations. There are more examples, ecosystem and so on. So you see there is this some list, okay? It's a very diverse list, from climate, organisms, human brain, infrastructure like power grid, telecom grid, this kind of thing, socioeconomic organizations like cities or societies and so on, and ecosystem like animal kingdom with the flora and fauna and so on. So what is the common feature of all these systems? So for example, if you take ecosystems, so you have many different animals, insects, and in their environment, these forests or deserts, wherever. And the way you can think about is the following, that these animals or insects, they are interacting among themselves. So you have different kinds of things which are interacting with each other, okay? And in an environment which is very complex, in the sense that you can have different kind of vegetation, different kind of water sources, and so on. So you have broadly speaking, what would be a complex system would be a network where you have, you understand network, right? So it can be a power network, it can be a network in the forests, where you have very different kind of objects which are interacting with each other. Sometimes those interactions are very varied because tiger would be interacting in a tiger in one way, but a tiger would be interacting with a deer in a different way, right? So similarly, you can have in a power grid different power stations, for example, transmitting information in different ways to other power stations and so on. So you have a network where you have these different objects which are interacting with each other in different ways, and there's a so large number of such objects and so large number of interactions that keeping track or making sense of it becomes very difficult. You can think about it, for example, this here is a complex system. So you have different human beings sitting here who will be interacting with each other in different ways. And then the question is, what is the best way that we can organize this set of people that are sitting over here? As in friends sitting together, enemies sitting apart, or some people who are in between or strangers sitting in some way. So this is also a social organization that one has to do. For example, in an office, if you have different sections, they have to work together in a cohesive manner such that you get the productivity that you want. So this kind of systems are there in different circumstances, and this would what constitute complex systems. Is this clear? Okay, fine. So another aspect of this complex systems typically is that these are very disordered. Disordered in the sense that different human beings are different, right? So it's not that all human beings are of the same kind. Somebody is speaking one language, somebody else is speaking another language. So there is a diversity, okay? There is a variation of traits and characteristics. So not all of them are of the same kind. So this is this sense of disorder, that not everyone is the same, or not every object is the same, okay? So this is a very typical feature, and we will try to see that if you have this diversity, what can be the consequences in some organization that we will try to discuss, okay? So then let me just, is there a duster somewhere? Yeah. Varun, you just keep track of time. I'll just lose. Okay, fine. Okay, so now we come to more mundane things. So let's, I mean, this you know, so this is complex systems. So the second thing is phases of matter. So you know gas, liquid, solid. I guess this is, at least in high school you have learned this, that there's a gas, there's a liquid, there is a solid. So a standard, and a gas, if you take a gas, for example, water vapor, if you bring down the temperature, it will first become a liquid. And then as you decrease the temperature even further, then it becomes a solid, which is, for example, ice, right? Now, the solids tend out to be of different kinds. One class of solids are what are called crystals. And the other class of solids, which we'll broadly call glasses or amorphous solids. So what is the distinction between these two kinds of solids? Okay? The distinction is the following, that if we look at crystals, if we take a microscope and peer into the crystal, then what we'll see is that the crystals have a certain spatial organization which is periodic. Okay, so the atoms or molecules, whatever, they form some kind of periodic structure. On the other hand, if you take these glasses or amorphous solids and so on, so they have very disordered structure. Okay, in fact, if you take a snapshot of this amorphous solid, snapshot as in you will peer into the microscope, just take a picture. Okay, and then you take the same solid, this same, for example, you have the glass, right? The glass there where you're drinking water. You take a snapshot of that, you take a picture, and then you melt that glass and take a snapshot. You will not be able to make any distinction between the way these atoms or particles are organized in the liquid and in the solid. Okay. So therefore, the puzzle that has been there, which is an unsolved puzzle, that how can we have, I mean, because people have been traditionally thinking that, you know, if I have a solid, I have this kind of organized structure, it's a crystalline structure, and that has certain properties and so on. This, for example, this idea that this rigidity, that if I hit like this, that something hits back on me. That's a rigid thing, rigid. So unlike a liquid where I can just put my hand through it, I can't put my hand through the solid, right? So there is a response. So this rigidity comes because of this ordered structure. There is some understanding of that. But where is the rigidity coming if I have this kind of a disordered structure? That is not clear. This is what everybody is trying to understand. Okay? This is the problem. Okay, so this is the distinction between crystals and, let's say, glasses and amorphous solids. So the kind of solids that let me focus at the moment is on what I would call granular solids. So what are granular solids? Just a pile of grains. Let's say sand. On the sea beach you go, you have a huge pile of sand that is there, right? So that would be a granular solid. Another example, like a broad definition of a granular solid, would be like toothpaste or foam. So you take toothpaste on the toothbrush, right? So let's say this is my drawing of the toothbrush, and then you pour the toothpaste on it, so it forms a heap, right? So for example, if you had poured water on top of the toothbrush, it would be flowing away, right? Or you pour honey over it, or any other liquid. On the other hand, if you put toothpaste on the toothbrush, it will form a heap like this, okay? So basically it can retain its shape. It's not flowing away. So that is also a property of a solid, okay? So there is this rigidity there. If you have any questions, please feel free to ask, okay? So these are called what I would call granular solids. The reason I'm invoking these granular solids is the following, that Now I can translate this to what I would call a packing problem. Okay. What is a packing problem? A packing problem is one, so for example, let me give you a box, and I throw some coins inside this box. Okay? So the question I'm asking is the following, that if I give you n number of coins inside a box of dimension L square, how many different ways you can organize those coins inside that box? Okay? So it's like a problem in a different way for a fruit seller when he's organizing the oranges and apples on display, right? So he's also packing the oranges and apples in a certain way that forms this kind of very balanced structure. Nothing falls apart, right? It's just like the heap of sand on the beach. There's no distinction between the two. Okay? So he has organized, and sometimes you see that the fruits are very well organized or ordered structure that are forming, but sometimes even if it is like a heap of tomatoes, it's not flowing away. It's still a heap of tomatoes, right? So you have this kind of packing problem, okay? So basically what we have is that we have these n coins which are inside this box, okay? So I can translate this problem in a different way, that I have the center of these coins, okay? So I can ask the following, that, all these coins have a certain diameter, right? Let's say the size of each coin is d, okay? And of course, two coins cannot penetrate each other if you are if you are doing on a tabletop, right? So then I can ask that I give you more and more number of coins. You have to find me a solution, a packing solution with the increasing number of coins, okay? So basically what you have to do, I'm giving you, I give you 10 coins, 20 coins, 100 coins, 1,000 coins, and you have to find a solution. So basically, in other words, what I'm asking you to do is to organize these points in such a way that the distance between 2 points is always d, okay? So the distance has to be, so if I write the distance as rij, okay, this has always to be equal to greater than equal to d. So I'm putting a constraint on the distances, okay? So then this becomes a constraint satisfaction problem. So the fruit seller is also doing a constraint problem, satisfaction problem in his own way, okay? In his or her own way. So you have to do it in this way, that basically you have to throw in these coins, and then you have to find the solution as I give you increasing number of coins such that this constraint is satisfied, okay? It turns out that if I give you coins of the same size, okay, that you will find a solution which has this kind of ordered structure, okay? So in 2D, this is called a hexagonal or close packed structure, this kind of structure, okay? Oops, I don't know what I'm drawing, but I'm drawing something. Anyway, so this kind of structure, if you have coins of the same size, you will always find this solution. This is the close packing solution that we'll find. Okay, this is the best that you can do. So there is some number, let's say, let's not get into numbers, but there is some packing, what we call packing density, at which you will get these kind of structures, okay? But suppose I start giving you 50 paise and, I don't know, 25 paise, or 1 rupee, 50 paise, 25, I don't know, now coins are all of the same size. It became pentagon, right? I can't, it's already a disaster, okay. So it should be a hexagon, okay. Okay, fine. So if I give you coins which are of different size, you will not be able to find this kind of organized structures, okay? There, the constraint satisfaction that you have to do is slightly different, because now, this is now Dij, where dij is equal to di plus dj by 2. Okay? So this is the constraint satisfaction that you have to do. Okay. Fine. So we as physicists, we do this constraint satisfaction problem in a different way. Okay. So this basically we are looking at packing problems. So what we invoke is this idea of mechanical equilibrium. At the end of the day, it's the same problem. It's just a different way of looking at it. So what is mechanical equilibrium? So mechanical equilibrium is very simple, that when you are going to the fruit cellar, nothing is falling apart. All the forces are balanced, and you have this very well balanced structure sitting over there. In other words, it translates to the following, that if I sum up the forces acting on all the particles, then this is basically 0. Okay? So this is the force acting on each coin, let's say. Okay? So typically, we can write the force as some gradient of some potential. Okay? So then this force balance solution translates to a minimum of this potential n. So this is basically what I call force, and this is what I call potential energy function. So in order to have this force acting on each particle to be 0, and the net force to be 0, it translates to that this energy function should be a minimum. Okay, so it's very simple to see that if I take a particles which is in a sort of like a parabolic trap, the force, the derivative over here is 0, and anywhere else, this particle would be just rolling downhill. Okay? So this is, let's say, for one thing. So how is this? Let's generalize this. Okay. So here, okay. So I have talked about, introduced this idea of mechanical equilibrium. So what I'll now introduce is this idea of a potential energy landscape. Okay, so this is slightly, this is the main thing. So basically, what is a potential energy landscape? So suppose you think of the following, that some ant is walking. Imagine that some ant is walking, and this is in 2D space. So each location of the ant is, let's say, given by some x1, y1 to xn, yn, right? And at each point, I can measure the energy of the ant, let's say. Okay. So then I can plot the energy in xy space, and these would be, each location of the ant would be a different point on this space. Okay. Now, what I have is, now I have many ants or many coins. Okay. And if I am in d dimensions, and I have n number of ants. So this potential energy landscape is embedded in this dimensional space. Okay? Is this clear? So basically what we have is, let's say I had these coins, and let's say the locations are R1, R2, R3, Rn. Then I can write an energy function which is U R1, R2, R3, Rn. Okay? So this constitutes a potential energy landscape which is embedded in this space, dn dimensional space. Okay? So when we are talking about, and therefore, I mean, if you think of this, imagine that you take this box of coins and you're shaking them. Okay? So every snapshot, let's say, would be different points on this dn dimensional landscape. Clear? So when we are talking about mechanical equilibrium, so it essentially means that I'm looking for that minimum in this large dimensional landscape. Okay? So if you have, let's say, 100 coins in 2D, so it's this landscape which is spanned in this 200 dimensional space and so on. Okay? So finding a minimum is, let's say, a non-trivial job. Okay? In most cases. It turns out that if I have coins of the same size, then typically there is a very well-defined minimum, and I mean, so this, let's say, I drew this picture of this particle in a well. So typically you would have some, in this large dimensional space, a well-defined minimum, which would correspond to this, what I would call a crystalline structure. Okay? Fine? So if you have coins of the same size, then in this large dimensional space, you have this function has only one minimum, which corresponds to this crystalline structure. Okay? But now suppose you have coins of different sizes. Then what happens? So then it's where all the fun begins. So to get to the fun, so what we'll do is introduce this idea. So I have introduced what we call potential energy landscape. Now I'll introduce this idea of frustration. Okay? So suppose I have, let's say, a triangle like this. Okay? And I have some arrows which are sitting like this, which can either point up or point down. Okay? Now I have a function which is like, let's say, where sigma is equal to plus minus 1. Okay. So this function is a minimum when all the arrows are pointing in the same direction. Okay. So if you take plus plus, you will always get minus j with some factor. And you get minus, or everybody is minus, then you will also get minus j with some factor. Okay? So this is the case when j is positive. Okay? But when j is negative, then what happens is that to satisfy one bond, I will have the situation where one guy is up, another guy is down. Okay? And then the question is what happens here. So if I have, so if j is negative, then in order to this number to be negative, both needs to have different signs, right? Is that clear? Yeah. So now the question is, I have satisfied one bond, what happens to the other bond? Okay. Because if this guy is up, this guy needs to be down. If this guy is down, this guy needs to be up. Okay. So that, I mean, you cannot solve the problem. Okay. So this is this idea of frustration. That this guy is frustrated, that basically he doesn't know what to do. Okay. So similarly, that if I have coins of different sizes, okay, and I try to satisfy this constraint that Rij is always greater than equal to Dij, I will never be able to find that perfect structure because I will always land up in this kind of frustrated situations where I don't know which is the best case scenario for 2 coins to sit next to each other, or let's say 10 coins to sit next to each other. Okay, this is very characteristic of disordered systems, this sense of frustration. And you know this is also in society. You are always frustrated with different things. You will never find the perfect solution. Okay? All solutions are imperfect. Okay? And this you can see in very simple constructions, that if you have this kind of situations, frustration is a very natural thing that happens in frustration in this physical sense. Okay. So the consequence of this is the following, that if I now look at this potential energy landscape in this very large dimensional space that I talked about, okay? So there, it turns out that this function, which is okay, maybe I'll just, so firstly, how do I compute this function? I mean, I have not told you how do I compute this function, right? So this is where this idea of models come into the picture, or modeling comes into the picture. That as physicists, we have to cook up some interaction between object 1 and object 2, okay? With the hope that whatever interactions I am cooking up, and I do my calculation using those interactions, then I compute some quantity which we call, let's say, observable, something that I can measure, like energy or pressure or whatever, something, or I mean, I can think of many things, but if I tell you, it doesn't translate properly. So for example, I can ask if let's say I have these coins, and let's say I write down some function which models this interaction between these 2 coins, then at the end of the day, I can ask that if I put some load on this packing and measure the resistance that the packing is providing. So for example, if you take a pile of grains, then you put a load on top of it, you can see how much is, or think of it in the other way. So you have a pile of grain, you are measuring the weight of that. So it will have a certain weight, right? So depending upon the kind, I mean, if you have steel balls, you will have a different weight. If you have sand, you will have a different weight, and so on. So whatever you are measuring, that measurement or that observable, you should be able to predict or compute using the model interactions that you have placed inside the system, I mean, inside your calculations. So this is the entire idea of modeling, that basically I don't know what's happening over there, but I think of something, and then I do my calculations and see whether my model has given me the answer that I'm looking for. In most cases, that answer is wrong. So I have to find a better model. Okay. So for example, this function that I have written over here, so what typically one does is that one writes it as a sum over pairwise, so basically some function which is dependent upon the distance between 2 coins, okay? And let's say I take this function as something like some stupid function, let's say something like this. I can choose this, okay? So if any questions? So if I choose this function and feed it into here, I can compute some number if I know the distance between the coins and so on, okay? So then I can compute this function for different, let's say, realizations of this collection of coins. And then I can, let's say, for example, I can, for this, what we call the potential energy landscape, I can try to construct that, right? In principle, I can try to construct that for different realizations of these coins. Okay? Firstly, figuring out all those snapshots. So suppose I've given you n coins and I've given you a box of L square. Okay? Finding out all those possible realizations of this n coins is a non-trivial task. And typically you have to do that numerically. I mean, you can't do by hand, okay? And then trying to find the organization of the coins or the locations R1, R2, R3, or whatever, that will minimize this potential energy, that is also a non-trivial task, okay? So typically you have to do, so one is, typically one has to do some numerical minimization. To find the best, the minima of these function, for example, okay? So it turns out that if one were able to find out the minima of these functions, okay, of this function, then it has a very interesting structure. This landscape has a very interesting structure. So basically, if I do a projection in this space, let's say this is my potential energy, and this is my coordinates. So typically, it has a very rough shape, landscape. It's like Himalayas, okay? A lot of valleys, local mountains, local hills, and so on, okay? So what we call, it's a very rough landscape. And then also, one can ask the question that how many number of such local minima are there, okay? And that gives a sense of the complexity of the landscape. And typically, this is e to the power of n, where n is the number of coins inside the box, okay? So this number of minima, so the more the number of coins that you have, more the number of local minima that you will get. So it's fun because you have this very rough landscape and you can spend all your time walking along this landscape, if you like mountains, of course. Okay. So what was so we talked about this guy at the beginning who won the Nobel Prize in 2021. So he asked that if I look at the snapshot or the configuration which is sitting at this local minimum and the configuration that is sitting at this local minimum, are they different? Are they similar? How much similar, how different they are? Okay, because this is a valid question to ask, right? So I have different realization of these coins here, another different realization of the coins here, how different they are, how similar they are, and so on. Okay. So the function, I mean, the quantity that one looks at is what is called an overlap function. So I'll just so basically what do? I take one snapshot, so snap one, and let's say I take snap 2. An overlap just means that I put snap 2 on top of snap 1 and ask how similar or dissimilar these two snapshots are. So what I can do, let's say the simplest thing that I can do, I can just take a grid, and I can say that wherever the center of the coin is, that I'll put as 1. And if the coin center is not there, I'll put 0. So I have a set of 1s and 0s. I have another set of 1s and 0s. I can put one on top of the other, and I ask how similar or dissimilar these two structures are. And this is given by this overlap function. Okay? So what Parisi found was that this matrix, this overlap matrix, if I think about it, so it has a very interesting structure that so it has this following thing. So in this here, I'll have, let's say, some Q1. And this sector has this sort of Q2, and zeros sitting over here. So basically what it's saying is that I have two overlap values, Q1 and Q2, where Q2 is greater than Q1, okay? So there are some local minima which are very different, which have very little overlap, and some local minima which have very large overlap, or basically if I take two snapshots, they have very close or very large overlap in some cases, and in some cases, they have very little overlap, okay? And then you can ask that, so if I go back to this landscape, some rough landscape, it turns out I can do a grouping that so if I call each of this a basin, then I can do a grouping, let's say what I'll call a meta basin. So within a meta basin, I'll have all these snapshots that are sitting over here will have a large overlap. And if I choose another meta basin, then a snapshot from here will have very little overlap with the snapshot over there. Okay, so this is the kind of organization that is emerging within the potential energy landscape. If I have coins which have different sizes, okay. So then, so this is what is called one-step replica symmetry breaking, but let's not bother about that, okay. So then what the further conjecture that he made, or he tried to show in some models, is that if I look further, that if I zoom into one of these basins, I can still find more finer structures that this square over here, this quadrant over here, will break up into, so I can draw pictures like this. So initially I had structures which are like this. Okay, now I can go inside one such, so this was one meta basin. And now if I go inside one meta basin, I can find, again, finer structures like this and so on. Okay? So this is a very rich organization that we are finding inside this potential energy landscape. Or if you are going into the mountains, so if you go into a valley, and then you will find more valleys inside it, and then you go below, then you find more valleys inside it, and so on. So this is at the level of a conjecture, okay? Or shown in some simple models. So what many people are now trying to do is that if I take models of physical systems like this box of coins, is it true that we have this kind of very nice organization within this landscape, okay? So it turns out that in some examples we are able to, or some people have been able to explore and demonstrate that indeed, if I compute this overlap function, this matrix will have this kind of a structure, okay? So this is basically an exploration of this potential energy landscape for disordered systems. So this is, or in other words, this is the organization of the potential energy landscape of disordered systems. that you have a very rough landscape, okay, in this very high dimensional space. So in the case of the crystalline systems, you would have typically one local minimum. But if you have these disordered systems where you have coins of different sizes, or it can be very diverse. So I can now translate this into other kind of disordered systems and conjecture that if I could compute energy functions so it can be in power grids, it can be in ecosystems, wherever be it. Okay? If I could compute these energy functions, then the corresponding energy landscape would be having this kind of a structure. Okay? So this has been, this continues to be a very interesting area to explore, to find for diverse systems whether you have this kind of landscape or not. So at some level, this is still a conjecture where you still have to prove in different systems or exploring different systems and find that indeed this has this structure or not. So this is one set of problems that people do. Okay. So the next set of problems that people would like to do is the following. That now I have given you this box of coins. Okay, which has this kind of a very complex potential energy landscape. Then what I do is I just shift one of the coins by force. Okay. Then I ask, how does this box of coins now reorganize itself? Okay. So basically what we are asking now is the following, that if I have this local minimum, this very rough landscape, I start from here, I do this perturbation, and then I ask, how does this system go from this local minimum to this local minimum, and so on. Okay. So what happens? Let's say, let's take a simple example. So what happens is that if you do some kind of a deformation in this box of coins, what essentially it happens is that you are tilting the landscape in some way. So basically you had some, I'll write in with some other variables. So my original potential energy function was u. Then I have this new potential energy function, which is u prime, which is some, let's say this is my deformation that I'm doing. And this is the force or stress that is emerging inside this. Let's not bother about it at the moment, but this is the deformation variable, or how much force that I've applied, or how much tilt I've applied into the system, and so on. So if I have this new potential energy function, then what essentially is happening is that as I increase the more and more the deformation, so I have this kind of a, let's say, local minima initially. So at some point, as I tilt this local minima, this minimum will vanish, and the system will just roll downhill and go into this new energy minimum, and so on. Okay. So basically, I have destabilized one of the local minima, and I have jumped into the next local minima, and so on. And then I can ask that if I take now these two local minima and see what is the distance, or how much, what has happened to this box of coins as it went from here to here, right? So it went from minimum 1 to minimum 2, okay? So then what we find is the following, that it could happen that in some cases there is only some local rearrangement of these coins happening. Okay, so basically if I had 4 coins sitting over here, so let's say what could happen is that the small coin goes over here, the bigger coin comes over here, and something like this has happened. Some local reorganization has happened. Okay, so and that is sufficient enough, this local reorganization is sufficient enough to jump from one local minimum to another local minimum. Okay. And then, you can compute, for example, the amount of distance a coin has traveled and so on. And so that has also very interesting structures in space and so on. If you are interested, I can discuss that later and so on. Okay, so this is one class of problems that people are interested in, that if I start putting some mechanical perturbation into the system and ask how does this landscape get transformed as I'm putting this external perturbation or this mechanical perturbation, and then ask what are the local reorganizations that are happening and what are the consequences and so on. Okay, so you can, I mean, again, going back to the mountains, so landslides are very common, right, in the mountains, or avalanches. Okay, so even we can translate that language over here. So for example, when this thing is jumping from one local minimum to another local minimum, sometimes what will happen, we will have a huge event which happens inside this configuration, that as I go from one local minimum to another local, so you can think of it in the following way, very crudely, that I had one metabasin over here and I have another metabasin over here. Then as I jump from one metabasin to another metabasin, I can have an avalanche happening inside the system. That a large-scale reorganization of the coins will happen for the system to go from one metabasin to another metabasin. It's exactly like the avalanches that you have in the mountains and so on. Okay, the huge event has to happen for the system to go from here to here and so on. Okay. Okay. So the last thing that I will tell you about is So far we have talked about the organization in this potential energy landscape. We have talked about if I do some deformations on the system, in the physical system, how that translates to changes in the potential energy landscape. The last thing that people have started to become interested to know is that, so suppose I started off with this problem, that I throw some random points in space. So again, let's go back to the initial constraint satisfaction problem that we talked about, that I throw some random points in space, and eventually I have to find this solution where Rij is greater than or equal to Dij. Okay, so this is the solution that I have to find a solution which satisfies this constraint. Okay, so I started off with points which are randomly thrown in space. Okay. And of course, this constraint will not be satisfied. Okay? So then I can ask the question that if I start from this initial configuration, initial state, how will I reach my final state? So what essentially the question that I'm asking is the following, that as I told you, that to find the final state, I have to minimize my potential energy function. Now, essentially, the question that I'm asking now, that how do I go from the initial state to final state, is basically asking how this minimization process is happening. Okay? So basically, I have started off, again, somewhere in the high up in the mountains, and have to reach a low-lying valley. Okay? So then I can ask that how, as a function of time, let's say I compute my mean velocity, let's say. How fast am I moving? Okay? And I ask, how does this behave, or how does this quantity behave? Or how fast am I moving as I'm going to this, from the initial state to the final state and so on. So it turns out this is not some, well, it's a simple function in the sense it's a power law. So if I put log V, so basically this V thing will go as some t to the power of beta. Okay. And basically it is telling me that, and what happens is that, so if I have smaller systems, there is a cutoff like this that it will suddenly find this local minimum. But if you have larger, as you go to larger and larger systems, the time scale, or the time to find a local minimum, essentially diverges. Okay? Or if you have, let's say, this is numerical problems that we face. For example, if I give you 1 million coins, okay, and you start off with this very random state to begin with, within your computational lifetime or your cluster lifetime, how long you're running your job on the computing cluster, you may not be able to find the best local minimum. Okay, that is the state of art minimization, numerical minimization that we can do. But it tells us a lot of, but it is still giving us a lot of information. It is telling us the path that you are taking along the mountains as you are trying to find the local valley. Okay, so we can look at so as this optimization problem is proceeding, or as this minimization problem is proceeding, you can ask, which pathway am I taking? What are the local valleys that I'm encountering? What are the structures that I'm encountering? Okay, and now, I mean, you have to do this for different problems, and these are things that people are doing at current moment. And then you can ask, as one structure is transformed into another structure, what are the changes that are happening in the structure and so on. So I hope, I mean, there are a lot of other things that one can talk about. So in the context of these disordered systems, the one essential idea is this idea of the potential energy landscape. And it has this very complex structure, which comes out of this idea of the frustration. And there are a lot of things to do to understand this mountains and landscapes. And yeah, so basically, people are still exploring and trying to find different properties. So basically, you are asking that if suppose I start from here and I want to look around and walk around and see how my neighborhood is, I found that, and then I go again to the next valley and then see how my neighborhood is. Now I want to find what is the best path from, let's say, point X to point Y, okay, in this landscape. So that these are also questions that we need to answer. And maybe in this process, we will be able to find also, in some contexts, better materials, in the sense that if I can now tune, if I know the kind of landscapes that I'm getting, the kind of paths that I'm taking while I'm doing certain kind of perturbations, then I can tune my system in such a way that, for example, let's say I'm trying to find piece of, let's say, or a heap of grains which has a certain property, okay? So if I can figure out that what are the properties of the landscape that gives me this physical property that I have, then I can perhaps tune my ingredients in such a way that the landscape properties are such that I get the functional property that I'm looking for. I don't know whether that translates well to you, but if you, I hope you can make some sense of it. So material design is also, in some sense, an attempt to trying to understand potential energy landscape properties and also to improve upon the potential energy landscape properties. Okay, I think I'll stop there.
We have a few minutes for questions, maybe 2 or 3 questions.
Everybody understood everything, which is good. Or nobody understood anything, that's even better.
So I have a question. So you had those coins which were all circular, and then you decided that you wanted different sized coins. What if you have different shaped coins?
Yeah, that's.
So does the landscape look similar?
Of course, of course. I mean, of course, I don't know priority the complexity of the landscape, but yeah, I mean, for simplicity, I put just shapes, 2 different sizes. But of course, yeah, I can have different shapes, and then makes life even more harder, even more hard. So yeah, so that's non-trivial. I mean, this one problem that we are looking at the moment is a very simple problem, but a packing of rubber bands. So that's not an easy problem if you think about it. So you have these rings which can go into each other, and then to find the best packing, that's a very non-trivial task. I hope you guys get excited on packing problems in the future. That's practical also. You have to find a way you best pack your suitcase for the landscape.
Any Other questions? Okay, but so we'll break for tea. We'll thank the speaker once again. And we'll break for tea, but when you come back, you'll have to have many more questions because the next whole session is all based on your questions. Yeah? So over tea, make